right, team. Settle in. Production patterns. 10 Amazon Web Services decisions. Senior engineers get right looks intimidating on paper, but it boils down to a handful of decisions you can master today. A junior engineer's design ships to production on a Friday. 6 weeks later, a bot scrapes their access key off a public GitHub repo and quietly drains tens of thousands of dollars in compute before anyone notices. By the end of this video, you'll be able to make the 10 production decisions that separate the engineer who let that happen from the one who never would. Here's the thing most people miss. The difference between an engineer who understands Amazon Web Services as a platform and one who just memorized a list of service names comes down to a handful of recurring calls. Get them wrong, and you burn budget, break a service level agreement, or fail a compliance audit. Get them right, and your designs sail through review. You already know each of these services individually. Back in the shared responsibility episode, we drew the line between security of the cloud and security in the cloud. In the security services episode, we sorted GuardDuty, Inspector, Macie, and Detective into 4 distinct jobs. And in the network security episode, we separated security groups from network ACLs by the layer they operate at. Now we put them head to head, the way a design review actually works, not service by service, but choice against choice. Picture the room. It's late afternoon at CodeGorillas, and a junior engineer slides a design proposal across the table for review. The senior architect skims the first page, then stops cold on a single line, a managed versus self-hosted call that looks fine on paper, but would have the team patching servers by hand at 2 in the morning. That one line is decision number 1, and over the next half hour, the same 10 decisions surface again and again. The points where a reasonable-sounding choice quietly burns budget, breaks an SLA, or fails a compliance audit months later. These are exactly the calls we're going to walk through together. Here's the whole map, 10 scenarios, and underneath every one of them sits a single skill, matching the service to the job, not to the domain. Who patches the operating system? Which security service handles a finding? Whether to reach for CloudWatch, CloudTrail, or config, security group or network ACL, SQS, simple queue service, or SNS, simple notification service. Whether a task truly needs the root user, what trusted advisor covers, S3, EBS, or EFS, which pricing model fits, and finally, a role or an access key. Notice they're all the same kind of question. Where exactly does the boundary fall? Let's take them one at a time. Decision 1. The design runs the application on EC2, and nowhere does it mention who keeps the operating system patched. So you ask the engineer, and you get the classic answer. It's running in Amazon Web Services, so Amazon Web Services patches it. That's the mistake. EC2 is infrastructure as a service, which means the guest operating system is yours. Amazon Web Services secures the hardware, the hypervisor, and the facilities underneath, but the moment you launch an instance, every kernel update and every security patch on that OS becomes your job. An unpatched EC2 instance is not an Amazon Web Services problem. It's a customer-owned vulnerability, full stop. Amazon Web Services spells this out directly in the shared responsibility model documentation. The customer who deploys an EC2 instance is responsible for managing the guest operating system, including updates and security patches, plus any application software, and the configuration of the security group on each instance. There's no ambiguity there. The instance lives in Amazon Web Services, but the maintenance of what runs on it stays with you. So the real lesson is this: choosing EC2 versus a managed service isn't just a compute decision. It's a decision about how much responsibility you're keeping. And the patching line moves with how managed the service is. On EC2, the guest OS, the runtime, and the application are all yours, though Systems Manager Patch Manager can automate the work once you configure baselines. Step up to RDS, the relational database service, and the line shifts. Amazon Web Services now patches the OS and the database engine for you. Go all the way to Lambda, and Amazon Web Services owns the entire runtime. But notice what never moves no matter which service you pick: your data, your identity and access management, and your configuration choices are always yours. More control means more responsibility, and that trade is yours to make deliberately. Decision 2. A requirement lands that's clearly about security, and the team has to pick a tool. The mistake here is choosing by domain. It's a security task, so GuardDuty, Inspector, Macie, any of them should work, right? No, those 4 services are complementary, not interchangeable. They each do a genuinely different job, and they're designed to be used together. The way to pick correctly is to listen for the verb in the requirement, not the topic. The action word tells you exactly which service belongs in the answer. Here's the keyword map. When the requirement says threat or anomaly detected from logs, that's GuardDuty watching your CloudTrail, flow logs, and domain name system, or DNS, queries in real time. When it says vulnerability, or a specific CVE, common vulnerabilities and exposures, or patch level, that's Inspector. And remember Inspector's scope: it scans EC2 instances, container images in ECR, the Elastic Container Registry, and Lambda functions. It never touches S3. When the requirement is about PII, personally identifiable information, or sensitive data sitting in S3, that's Macie, classifying what's in your buckets. And when the requirement is to investigate or find the root cause after an alarm fires, that's Detective. One caveat to carry: Detective depends on GuardDuty being enabled first, because it investigates the findings GuardDuty raises. Decision 3. A production bucket vanishes overnight, and the first question in the incident channel is, who did this? The instinct is to reach for CloudWatch, because CloudWatch is the monitoring service and surely it saw something. But that's the mistake. CloudWatch measures performance, metrics, logs, errors, latency. It has no idea who made an API call. Asking CloudWatch who deleted a bucket is like asking the temperature gauge who walked into the building. The right service depends entirely on the question you're actually asking, and these 3 services answer 3 different questions. Think of it as 3 lenses. CloudWatch tells you what's happening: CPU, errors, latency, and it triggers auto-scaling and notifications when a metric crosses a threshold. It answers, is the system healthy right now? CloudTrail is a different lens entirely. It records who called what API, when, and from where. That's your who deleted the bucket answer. And Config is the third lens. It records what configuration changed over time and evaluates whether your resources still match your compliance rules. So when the question is who did it, that's CloudTrail. When the question is what changed and is it still compliant, that's Config. CloudWatch was never the right tool for either. Decision 4. A single malicious IP is hammering a subnet, and you need to block it. The engineer opens the security group and goes looking for a deny rule to add. And here's why that fails. Security groups are allow only. There is no deny rule to write. A security group can say who is permitted in, but it has no way to single out one address and turn it away. Blocking a specific attacker requires a control that can actually say no, and that's a different layer of the network. The virtual private cloud documentation draws the line clearly. Security groups are stateful, which means if you allow a request, the response traffic for that request is automatically permitted. You don't write a return rule. Network ACLs are stateless, which means responses to allowed inbound traffic are subject to your outbound rules. That word, stateless, is the one that bites people in production. The network ACL has no memory of the connection, so if you forget to allow the return path, the connection just silently fails. So the right tool to block that IP is the network ACL. On the left, the security group, stateful, allow only, attached at the instance, and return traffic is automatic. It simply cannot deny a specific IP. On the right, the network ACL, Stateless, supports both allow and deny, and operates at the subnet level. You add a deny rule there to block the attacker's address, but because it's stateless, remember to allow the ephemeral return port range, typically 1024 through 65535, for the response traffic. That's the step engineers forget, and then spend an afternoon debugging why a connection that worked fine through the security group is now getting dropped. Decision 5. An order is placed, and 3 separate services need to know: inventory, payment, and shipping. The engineer wires up a queue for each consumer, and writes code to push the event into all 3 by hand. That works until it doesn't. The reason it fails is that a queue is pull-based, and a given message is meant to be processed by exactly 1 consumer. Fanout simply isn't the queue's job. You end up re-implementing broadcast logic in your application code, and every new subscriber means another wire to solder. The right pattern broadcasts the event once and lets each service take its own copy. Here's the pattern that does it right. Start on the left, the order is placed. That event publishes once to a single SNS topic, which pushes a copy to every subscriber simultaneously. Now subscribe an SQS queue for each consumer. Inventory gets its own queue, payment gets its own queue, and shipping gets its own queue. Each queue holds a durable copy of the message, so if the payment service happens to be down when the order arrives, its message just waits safely in the queue until the service comes back. You publish one event, 3 services each get their own buffered copy, and adding a 4th subscriber tomorrow is 1 more subscription, no code change to the publisher. So here's the one-line rule worth memorizing. Fan out to many subscribers is always SNS. Buffering and decoupling work for 1 consumer is SQS. And when you need durable fan-out, broadcast plus a guarantee that nothing is lost if a consumer is offline, that's SNS plus SQS together. SNS on its own doesn't persist messages, so if a subscriber misses the moment, the message is gone. Subscribing queues to the topic is what adds the durability. Pause and notice what all 5 of these have in common. They're each about knowing exactly where a boundary falls: the patching line on decision 1, the verb that picks the right security service on decision 2, the split between performance, identity, and compliance on decision 3, who can actually deny traffic on decision 4, and who can fan out to many subscribers on decision 5. Same skill, 5 different boundaries. The next 5 go deeper. We're heading into root user discipline, pricing strategy that can halve a compute bill, and the single credential mistake behind one of the largest breaches in cloud history. Let's keep going. Decision 6. A question asks which tasks genuinely require the Amazon Web Services account root user. The mistake comes in 2 flavors: using root for everyday admin work, and assuming that common administrative tasks need root when they don't. Here's why that fails. Nearly all administration in Amazon Web Services can and should be done with IAM identities. The set of tasks that truly require root is tiny and very specific. Knowing exactly what's on that list does 2 things. It keeps you off the root user in daily operations, and it lets you answer these questions without guessing. Let's split it cleanly. On the left, the reliably root-only tasks. Closing a standalone Amazon Web Services account is the cleanest example that genuinely requires root credentials. Changing the root account settings, like the root email, password, or root access keys, requires root, and restoring revoked IAM administrator permissions requires root, because it's your way back in if you lock yourself out. On the right, the things people wrongly assume need root. Viewing the bill only needs billing access granted to an IAM user, and changing the Amazon Web Services support plan only needs IAM permissions. Amazon Web Services' own change support plans page spells this out directly, yet older question banks still get it wrong. Everything in day-to-day administration belongs to IAM identities, not root. And here's Amazon Web Services settling that support plan myth directly. The Change Amazon Web Services Support Plans documentation states that to change your support plan, you must have IAM permissions, not root IAM. This is worth flagging because a lot of older question banks still list changing the support plan as a root-only task. Current Amazon Web Services docs say otherwise, so when you see a Select 2 scenario about root-only tasks, closing the Amazon Web Services account is your safe pick, and changing the support plan is not. Decision 7. A review asks which categories Trusted Advisor checks, and which support plan unlocks the full set. The mistake is assuming every check is available for free on any account. It isn't. The full check set, along with the Trusted Advisor API, is gated behind your support tier. On the free tier you get only a slice service limit checks and a handful of security and fault tolerance checks. There's a logic to this gate worth understanding. Amazon Web Services uses your support tier as a proxy for how much optimization help you've signed up for. The more you invest in support, the more proactive guidance you get back. Once you see that the tier structure isn't arbitrary, the whole thing makes sense. Here are the categories to recognize: cost optimization, performance, security, fault tolerance, service limits, and operational excellence. That last one gives you recommendations for operating your Amazon Web Services environment effectively and at scale. When a question asks you to pick 2 categories Trusted Advisor covers, those 6 are your valid pool, and the gate sits underneath all of them. The full check set and the Trusted Advisor API require business tier support and above. I'd frame it as business tier and above rather than naming a single plan, because Amazon Web Services is reshuffling the support tiers over the next year. The principle is what's stable. The free tiers get only service limit checks and a few security ones, and you pay for the complete picture. Decision 8. A design needs to store files that several instances all have to share and read and write. The mistakes here are surprisingly common. Treating S3 as if it were a mountable file system, or writing a cron job that syncs files across instances with rsync to avoid setting up shared storage properly. Why does that fail? Because object, block, and file are 3 genuinely different storage paradigms, each built around a different access pattern. The right choice isn't about which service you've heard of, it's about matching the paradigm to how the data is actually accessed. 3 paradigms, 3 jobs. S3 is object storage accessed over HTTP. It's where backups, static assets, and data lakes belong. EBS is block storage, a virtual disk attached to a single EC2 instance in a single availability zone. That's your database volumes and operating system disks. And EFS is a shared file system, a network file system mount that many instances across multiple availability zones can use at the same time. So back to our scenario, files that several instances must share point straight at EFS, not a hand-rolled rsync job, and not pretending S3 is a file system. The shared file access pattern is exactly what EFS was built for. Decision 9. A steady production workload has been quietly running on on-demand pricing for a full year. Imagine CodeGorillas looked back at 12 months of on-demand billing on a steady service. They'd find they'd paid roughly 2 to 3 times what a committed rate would have cost over the same period. The mistake comes from both ends. Defaulting everything to on-demand overpays badly for predictable load, but overcorrecting and putting a database on Spot to save even more is dangerous, because Spot capacity can be reclaimed with just a 2-minute warning. The right pricing model is chosen by the workload's shape and its tolerance for interruption. Match the model to the shape. Unpredictable or spiky load goes on demand. Steady, around-the-clock load goes to savings plans or reserved instances. And fault-tolerant, interruptible work goes to Spot. The Y is on the right. On-demand is the most expensive rate, fine for short bursts, wasteful for steady load. Commitments cut costs significantly for predictable workloads, which is exactly what CodeGorillas left on the table. And Spot can be up to about 90% cheaper, because its spare capacity Amazon Web Services can take back at any moment with a 2-minute notice, which makes it perfect for batch jobs and a terrible idea for a primary database. Decision 10. And it's the one that's burned more real companies than any other on this list. An application running on EC2 needs to read from an S3 bucket. The engineer generates an access key for an IAM user and pastes it into the application config. Here's why that fails. Access keys are long-lived static credentials. They don't expire and they don't rotate on their own, so they leak. They end up in Git history, in build logs, and baked into machine images, and bots actively scan public repositories for them, finding leaked keys within minutes of a commit. That's not hypothetical. It's a routine cause of breaches. The senior pattern is simple. Anything running inside Amazon Web Services, an EC2 instance, a Lambda function, a container, uses an IAM role, never a hard-coded key. For EC2, you attach the role through an instance profile, and the application receives temporary credentials automatically. Those credentials rotate on their own, and crucially, there's no static key sitting in your code for anyone to leak in the first place. You can't lose a key you never created. There's one more layer worth adding. That metadata endpoint can itself be a target, so enforce version 2 of the instance metadata service, which requires a session token to read metadata. That single setting blocks the server-side request forgery attack that reached the metadata service and stole role credentials in the 2019 Capital One breach. Now, those role credentials are delivered through the EC2 instance metadata service, and Amazon Web Services advises refreshing them every hour or at least 15 minutes before they expire. Put the two together and you've covered both halves of the problem. Roles solve the key leakage problem, and version 2 of the metadata service protects the endpoint that hands those credentials out. So let's tie it together. Every one of these 10 is a service boundary decision, not a name to memorize. The senior engineer just knows where the line falls. The trick across all of them is to read the verb in the requirement. Who patches it? Who did it? What changed? Deny versus allow. Fan out versus buffer. Then match the paradigm and the model to the workload. Storage to the access pattern. Pricing to the shape. Default to managed services and IAM roles, and reserve the root user for the tiny list that genuinely needs it. Make these 10 calls cleanly in a design review, and your architectures hold up under pressure. That's what being a senior engineer actually looks like. Now let's put it to the test with a quick 5-question quiz. Question 1. A company runs its application on an EC2 instance, and a security audit asks who is responsible for applying operating system security patches. Is it A, Amazon Web Services, because the instance runs inside Amazon Web Services data centers? B, Amazon Web Services, because patching is always part of security of the cloud? C, the customer, because EC2 is infrastructure as a service and the guest OS is the customer's responsibility? Or D, it's split exactly 50-50. Pause here if you want more time. It has to be C, and here's why. EC2 is infrastructure as a service. Amazon Web Services secures the hardware and hypervisor underneath, but the moment you launch the instance, the guest operating system, including every security patch, becomes your responsibility, even though the instance lives in Amazon Web Services. Question 2. A security team needs to discover and classify personally identifiable information sitting in S3 buckets for a compliance report. Which service is purpose-built for this? A, Amazon Inspector. B, Amazon GuardDuty. C, Amazon Detective. Or D, Amazon Macie. Think about which keyword is doing the work here. If you said D, well done. The keywords are PII and S3, and that's Macie every time. Inspector scans EC2, container images, and Lambda for vulnerabilities, never S3. GuardDuty detects threats from logs, and Detective investigates findings after the fact. Question 3. An incident response team needs to find out which user deleted a production bucket, when, and from what source IP. Which service answers that? A. Amazon Web Services CloudTrail. B. Amazon CloudWatch. C. Amazon Web Services Config. Or D. Amazon Web Services Trusted Advisor. Lock in your answer before I give it away. The right call here is A. The question is who did what, when, and from where. That's the exact signature of CloudTrail's API activity record. CloudWatch only measures performance. Config tracks configuration state and compliance, and Trusted Advisor checks best practices. Question 4. An engineer must block a single known malicious IP from reaching all resources in a VPC subnet. Which control does it? A. Add a deny rule to the instance's security group. B. Add a deny rule to the subnet's network ACL. C. Remove the allow rule from the security group. Or D. Enable shield standard on the subnet. Run the decision rule from earlier before you answer. This one is B. Security groups are allow only and stateful, so there's no deny rule to write that rules out A and C. Only the network ACL supports deny rules and operates at the subnet level, so a deny rule there blocks the specific IP. Shield standard handles DDoS, not a targeted address. Question 5. A single order event is published, and 3 independent services, inventory, payment, and shipping, must each get a durable copy that waits safely if a service is offline. Which architecture fits? A. A single SQS queue that all 3 poll. B. An SNS topic alone with 3 direct subscribers. C. 3 Lambda functions invoked directly by the order service. Or D. An SNS topic with 3 SQS queues subscribed, 1 per service. Got your pick? Let's see. If you said D, well done. This is the durable fan-out pattern. SNS broadcasts the event to all 3 subscribers at once, and a dedicated SQS queue per service adds the durability, so each message waits safely if a consumer is down. A single shared queue would send each message to only 1 consumer, and SNS on its own doesn't persist messages if a subscriber is offline. And that closes out production patterns. 10 Amazon Web Services decisions senior engineers get right. The decision rules from today come back again later in the Amazon Web Services, the Amazon Web Services Certified Cloud Practitioner Exam Mastery, so keep them handy. See you soon.